We've had 4 videos on integrating with respect to x. And I said that dx matters, tells you what you're integrating with respect to. We can respect to x, integrate with respect to t, integrate with respect to y maybe. And let's see what kind of happens. Let's consider something that we haven't talked about at all. You might look at this and say, whoa, Jason, why are you drawing something that's not a function? My claim is that this is a function. It's not a function of x. Fails the vertical line test. But we can call this function u and say this function u is a function of y. Okay? For every y, this will give an x coordinate. For every value of y, this gives a unique x coordinate. You can say x is some function of y. That's no problem. And so what if I'm looking at this area now? All right, what if I want this area? Well, we can approximate this area with rectangles, right? What's the height of each of these rectangles? The height of each of these rectangles is x, the x coordinate of each of these points. X is the same as u of y, the function. What's the width of these rectangles? Delta y. And you can do everything we did in chapter 1 all over again. To say that the area, let's say we have n rectangles. Let's take infinitely many of these n rectangles. We can get a Riemann sum from I equals 1 up to n of this function evaluated at some place in that subinterval, in that ith subinterval, times that delta y. And that's true. That's all true. And you don't really need to focus too hard on it, but you can if you want. Everything we did for x can go for y as well. It's just kind of a reframing of perspective. Okay, there's a really good opportunity in this video to just rotate myself 90 degrees. And in fact, if I did rotate myself 90 degrees and you turn your phone, your tablet, or your computer monitor 90 degrees, this is going to look exactly like what we did in chapter 1. Okay, turn your head on the side. And it's just a regular old Riemann sum, just with the x's and y's switched. And that's all we're doing here. We're just switching the x's and the y's and doing things horizontally instead of vertically. Or maybe vertically instead of horizontally, depending on your framework for it. All right. That's what we're doing here. So this area, but under a area to the left of the curve, to the left of a curve, is the integral from c to d. You could use a and b, but convention is to say c and d, of that function with respect to y, dy. And that's what we're going to be using in this video. Because, of course, if the area to the left of a curve is this integral, well, then the area between two curves horizontally is just subtracting the areas. So it feels weird, but before the but, it feels weird. And you might be asking, Jason, what's the point? Well, I'm going to show you the point with the best way that I know. Laziness. Example 4. Now the astute math student will be like, wait a minute, flip through my beautiful pages of notes. We already did example 4, Jason. Well, it's so good, let's do it again. Okay, you remember example 4, we had a quadratic. This quadratic was y equals x squared. And we had a line. And that was 2 minus x. We were looking at the region between this yellow region. I think it was green back then. So now, if you will, turn that frown upside down. No, turn that graph 90 degrees, something that rhymes with graph. This phrase doesn't work, but look at it sideways. Instead of splitting this into two integrals, is this yellow region not just this blue region minus this red region, right? This yellow area is just the area to the left of blue minus the area to the left of red. We can do it as a single integral. Ah, nice. So just think about things vertically. Make our lives a little easier. Area to the left of blue minus the area to the left of red is how we're going to compute this. So the integral, oh, hold on. Area, if we're doing area to the left of a curve, we need a function in terms of y. But these are functions in terms of x. So we need to solve for x if we're going to do this method. So I guess it's simpler calculus, but it's messier at the start. So here, x is plus or minus the square root of y. Uh-oh, this is not a function. But since we know x is positive, for this region, x is positive, we don't care about this stuff over here. So let's just look at the positive portion, because on our domain, the positive portion is all we need. Great, so that's our red guy. And the other one is easier, right? Just add x to both sides, subtract y from both sides. Oh, it looks pretty similar. And in fact, that's because the inverse function for this blue graph is itself. But yeah, these are really just finding the inverse function. Anyway, that's neither here nor there. So we're going to take red. Oh, nope. We're going to take blue minus red. What are the y coordinates? What are our region of integration? Again, this is going to be blue minus red with respect to y. And the y values, again, I should really be precise here. This is our c. And this is our d. But what is y going from? Y is starting at 0 for this yellow region. And remember that foreshadowing music, I said this is the point 1, 1. Y is going all the way up to positive 1. One of the most... Yeah. There we go. Now we just calculate this integral. It has y's, but everything goes the same as x's, as long as this is also a y. Just think in y coordinates instead of x coordinates. Again, this is really just the area to the left of blue, so that's this whole area, minus the area to the left of red, which is that. And that'll give us the yellow area that we want. So the antiderivative is going to be 2y, because our variable is y, minus 1/2 y squared, that's the power rule. This is y to the 1/2, add a power, divide by that power, all evaluated between 0 and 1. So we get 2 minus 1/2 minus 2/3 when we plug in 1. We get a bunch of zeros when we plug in 0. So that's, get everything with a common denominator. 12/6 minus 3/6 minus 4/6. 12/6 minus 7/6 is 5/6. Hopefully that's what we got for example 4 the other time. Oh, great, we did. I was looking over here. Yeah, we got 5/6 last time too. Fantastic. And it was quicker, right? Last time we did example 4, it was 2 pages. And we had to split up the region. This time, there's only 1 page. Maybe I wrote a little smaller. But yeah, sometimes they'll both work. I'm never going to force you to use one or the other. But sometimes one of them is going to be easier. And that's kind of some of the funner, more interesting homework problems, in my opinion, is they won't tell you which one to use. Sometimes they'll tell you, and sometimes they'll say, choose your own way. And even when they tell you in the homework, you can choose your own way anyway. All right, let's do the last example, example 5. Find the area between x equals y to the 4th and x equals y to the 5th. So y to the 4th and y to the 5th look a lot like x to the 4th and x to the 5th, just sideways. If you switch the x's and the y's, that's reflecting it around a diagonal line. Usually switch these things sideways. Inverse functions. Remember that from p-calculus. So x to the 4th kind of looks like a flat parabola. The y to the 4th is going to be kind of a frat parabola. Kind of a sideways flat parabola, kind of like this. And again, we know that what x to the 5th kind of looks like a flat cubic function. The y to the 5th will also be a kind of a flat cubic function. And it's maybe not super obvious which one's going to be on top where. You don't have to graph this by hand. You can just go over here. X equals y to the 4th. And x equals y to the 5th. And you can say, Jason, I can't see anything. That's okay. We have to reset our scale. Go from -1 to, no, -2 to 2 maybe. Great. We're looking for the area between these two curves. You can see that they intersect right here. We don't care about any negatives actually. And let's zoom in a little bit to make this a little easier to see. The area that's the only region that's trapped between these two curves is right here. And let's change the problem because I want to show something very important. Okay. Let's change the problem to have 2's in front of these functions. Because it shows off a very important distinction. So if we copy this down, the 2y to the 4th is the blue graph. And so the cubic type one is above it. But there's an intersection. And it looks kind of like this. I'm exaggerating the difference just to make it easier to see this region. This is our region that we're looking at. All right. So this is intersecting at the point 1, 2. Let's see, or at the point 2, 1. You can use Desmos to help with this. So again, we're looking at this region. Let's use yellow again. So there's 2 ways of doing this. You could have this in terms of x or in terms of y. You could do area under blue minus area under red. Right? Area under blue minus area under red. Or you could do area to the left of red minus area to the left of blue. Up to you. It's already written in the form. Think about it as area to the left. It's already solved for x. But you could switch things around and do what we did in the last example and switch it. The important thing is that you remember which x or y coordinate to use. We're looking at areas and integrals with respect to y. We need y coordinates. If it's stuff with respect to x, it's going to be x coordinates. As a side note, remember function transformations? If I multiply a regular old function by 2 on the outside, that doubles it vertically, stretches it vertically. But now we have functions of y. So if I double it, it's actually going to double it horizontally. And that's why it's 2, 1 instead of 1, 2. So if we have things in terms of y, we're going to have the integral of the red function. That'll be everything to the left of red. And again, if you choose wrong, you'll just get a negative answer and you can switch it. As long as it is a single region, you may have to break the region up into multiple pieces. Of the red guy, which I need to color code it over here so I can remember. Red guy, which is 2y to the 5th, minus the blue, which is 2y to the 4th. And then y, well, we're looking at the yellow region. The y, the smallest y gets is 0, and the biggest y gets is 1. X goes from 0 to 2, but y goes from 0 to 1. And don't write dx here. Don't be silly. We're taking the integral with respect to y. Power rule says add a power, divide by that power. Add a power, divide by that power. Evaluate from 0 and 1. And we'll get 2/6, which is 1/3, minus 2/5, minus a big fat 0, and we evaluate this. Get a common denominator, multiply by 5 over 5, 3 over 3. Get 5/15 minus 6/15. Wait, did I choose the wrong one? Wait, did I copy the graph down wrong? Because this is negative 1/15. Another perfect opportunity to show you what happens if you choose your functions in the wrong order. Yeah, if you choose wrong, don't worry. The answer is just the positive version. Hold on. This orange one is the one to the 5th. The top one should be the 5th. Oh, I graphed it wrong over here. Wait, no, I didn't. I did it right. Top one is the 5th. Oh, I color coordinated it wrong though. This is red. And this is blue. So that's what we did in the opposite order. The graph is right though. But color coordination's important. I even had it read there correctly. Well, excellent opportunity to show you guys what happens if you choose wrong. Still get the right answer eventually. Because I did the blue area minus the red area, but the red area was bigger. Great. Excellent job. With that, go and enjoy some homework problems. Hope you caught the error. There will be more to come. Bye-bye.